This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Well, hello, I'm Lee Bortons, and it's Wednesday, December 4th, 2024. Welcome to the Math Map Book Club, where Kirsty Gilpin and I discuss lessons each week from our math curriculum for families with students enrolled in classical conversations communities. This year, we have helped successfully, I think, navigate the first semester ever of Challenge A students using the curriculum, thanks to Kirsty and Babs and Shauna and the team that we have here. And I'm just really appreciative and thankful for that, not just because it's Thanksgiving, but you really have done an amazing job. So, Kirsty, I look forward to everybody's questions today. And, we were talking about since Q&A coming up, we might not have very many people. Look at them. They're there.
They are. This is so exciting. All right, I am going to share my screen. Find the right buttons. Okay. I have all these options. I'm always hoping I pick the right one. So, so I have created a couple of slides, but really the time is here for all of you. So, I thought I would share because a lot of you, I think I have it written somewhere. And so you may have read or heard me say that there's mathematics education, mathematics in general is a lot more like climbing Mount Everest. That there's a lot of work you have to do before you really get that amazing view. But once you get it, it's great. And one of the things that CCMM is doing is reading Listening for Heaven's Sake. So that's what I've got on the screen there. And there was this piece in here, and I just thought it was really applicable to our math journey. And so I thought I would share this with you. He says that many people try to tackle the besetting problems in their lives all at once. They're like rookies trying to ascend Mount Everest. They just don't have the understanding or experience in mountain climbing necessary to reach the summit. Those who make it up Mount Everest generally start out slowly. They first find an experienced guide who assists them in learning basic safety measures and mountaineering skills. Then they spend time climbing the low elevations with dedication until they learn to handle all of the challenges and obstacles. And finally, they make it to the top. After years of climbing and learning, the student may be able to become a teacher and help others learn to climb mountains too. Those who try to skip the beginning or the in-between steps and undertake the climb alone or unprepared can get into real trouble. Some merely give up in frustration and disillusionment when confronted with the hardships of the climb. Others are killed or permanently scarred by the experience. In any case, without mastering the basics, we will never become master climbers and reach the summit.
Good.
And so it's applicable to a lot of things, obviously, but I've often felt that way about math being like climbing Mount Everest. And so I just really loved that idea that climbing Mount Everest really needs helpers. And so that's one of the things that we're doing with the book club is, and I just realized what I did to you, I'm so sorry, is helping one another and hopefully equipping you to be able to help your students. And so just thought I would share that. So the next thing we are going to talk about are your questions. We have a couple of other things that we can talk about, but our goal this week really is to answer any questions that you have. So did anybody come prepared?
Well, I would love to know more about limits and asymptotes. And I say that like a couple weeks ago we were talking about functions and somebody asked the question again, can you explain again what a function is? And I said, well, why do we care? And I want to, I mean, I do care, but you gave a really good explanation, Kirsty. And so that's kind of how I'm feeling about asymptotes and limits right now. Not really why do I care, but like I just don't get where they come from or what like I just don't have any understanding of them.
I can understand that. I'm going to pull up a whiteboard that's going to be better than the PowerPoint slide here. Let me just, can everybody see that? The pink screen instead of the questions?
Yeah.
So limits and asymptotes somewhat go together, right? Although limits is a broader idea. And
Okay.
what a limit does is it lets us get close to something, right? So thinking about climbing Mount Everest, right? There's a limit to how close you want to get to the edge or how far you want to lean over, right? Before you fall off the mountain, right? There's a limit to how high you want to climb before you start supplementing your oxygen, right? There's all of these physical limits that are around us. And I don't really want to know what it feels like to be high on a mountain without oxygen, right? Like, I don't really want to fall over the side of the mountain and tumble far down below, right? So I can't go past, right? I can't go to that place. And so I say, well, what happens is I get really, really close to it, right? And so perhaps I notice it as I climb up a mountain. And then anybody that's from a low state that goes to Colorado, for example, right? And you go up like Pikes Peak, you can drive up Pikes Peak and you get really high and you can actually start to get that sense, that altitude sickness, right? You haven't actually gotten to the place where you're going to die because you don't have air to breathe, but you're getting close. So you're saying, okay, I haven't gone all the way to where I'm going to die, but I'm getting close to this. And what happens as I go up the mountain? I'm starting to notice these physiological changes, right? What happens when what does the view look like if you're standing right on the edge? Well, I can't stand right on the edge, but as I get closer and closer to the edge, right, I see this view becoming more and more expansive and I can see farther and farther down. And so I can get a sense of what would it be like, right, at that place I can't go to by looking at the pattern as I get closer, right? So that's the whole idea behind limits. And so mathematically, right, what are we saying? So one of the most famous limits, right, is something like this, right? If I was to look at 1 over x, right? What value do we say x cannot be equal to?
0.
0, right? That's our edge. That's our oxygen zone. That's our edge. That's the place we can't go to because we don't really know what happens there. But I want to know what happens. What do I think would happen there, right? How can I look at that? So that's where I say, well, what happens if I get really, really close to 0, right? What would happen? Well, then all we're really doing is saying, okay, well, if x is 1, 1 over 1 is 1. Pretty safe. Well, what if I go a little bit closer to 0? Let's say x is 1/2. So now I have 1 over 1/2, which is 2. And then I say, okay, well, let's go halfway again, right? We could just keep going this way. And notice our pattern here. And then let's say, well, I'm going to go 9/10 of the way there, right? So what if x was 1/10? Right? Well, 1 over 1/10 is 10. And now I say, okay, well, those are still numbers I can kind of comprehend. And if I was to look at this graph here, right? Here's my 1. So I've got my 1 was 1. And I'm gonna kind of smudge this like it because I don't have enough room the way I drew my graph, right? So my scales are not necessarily equal. But let's say that was 1. Well, at 2, it was 2, or at half, right? At 4. And at 1/10, it's 10. Well, what would it be at 1 if x was 1,000?
It'd be 1,000.
It'd be 1,000, right? It would go way up here. What about if x was a million? a millionth.
A million.
It'd be a million, right? So as I'm getting closer and closer to zero, right? As my x value is getting closer and closer to zero, my function is doing what? It's
Really
getting bigger and bigger and bigger, right? And so I can't really say what happens at 1 over 0 because, right, although we can talk about it, right, when we calculate, we say it's not defined. And so there's not a value when x equals 0, but I can say, man, as the closer I get to 0, and we can never really get there, right? I mean, I can always go another 90% towards 0. I can never really get to that number right before 0. But the closer I get to 0, the bigger that number gets, right? And so that's why I say, well, there's no limit, right? There is no limit. The closer that I get to 0, this is just unlimited. It's headed towards infinity,
And so you
right?
would say the limit of x as x approaches 0 is infinity.
Yeah, well, the limit of 1 over x or 1
Oh,
divided by
right.
x. Yep.
Right. The limit of 1 over x. Okay. Okay. So all of these, when we read limits in the math map, are those all givens? Like this thing you just showed us is a law, kind of like it's just, or not a law, but let's see. Because the denominator can't be 0, this is an inherent limit in a function,
Right.
division,
Yeah. So, yeah, sometimes, right. Now, I could say to you, what's the limit as x approaches to 2x, right? Well, as when x is 1, 2x is 2.
2.
When x is 1/2, 2x is 3. As I get, as I'm approaching 2, what's my limit? What's 2? Can I put 2 in for x?
No, because then you're equal to 2. Well,
Well,
I
but I can, right?
can. Okay.
I can because there's no mathematical reason why x can't be 2,
Okay.
right?
Right.
So I can say
Right.
what happens. So as x is approaching 2, what, right, as it gets bigger, what's the biggest number I could get?
4.
4. So here, right, we just picked a number. We've just picked some number and said, hey, as x is approaching 2, what's the biggest it can get? The biggest it can get is 4,
Okay.
right? And sometimes we're going to look at, sometimes we're going to look at our limits in these cases, right? There are going to be times where we say, okay, well, what is the limit of something like this? But where their usefulness and where their helpfulness comes in is looking at cases that we cannot just calculate, right? So I can't calculate 1 over x when x is 0, right? But I can look at those numbers really, really close to say what would be happening, right? What's the limit? What's the biggest it can get or the smallest it could get, right? So for example, I'm gonna
But
sneak
you could
this
do
in
like a
down.
real life example where population growth charts use this a lot. So say the limit of the average woman is 6 children in a lifetime. Then you can do statistical math as more and more women or fewer and fewer women approach the limit of the number of offspring who live. Like there's so many applications for this besides 0.
So I was just gonna say, right, mathematically, right, we could look at this case here, right? We could still look at 1 over x, but now instead of looking at x as it approaches 0, what happens as it approaches infinity? Right? So now instead of making my x smaller and smaller and smaller, heading towards 0, what happens as my x gets bigger and bigger and bigger? Right? So if I'm dividing by bigger numbers, what happens?
You're getting a smaller and smaller.
I'm getting a smaller, right? So here, I'm gonna use red for this one. Here's where we would have our asymptote. And our asymptote is a visual representation. All right, X is that 0 is excluded from our graph, right? We're not going to use X equals 0, and it's not going to correspond to a point on our graph. In this case here, right, the limit is 0, but does 1 over X, can it ever be 0?
I don't think so.
No,
So
right?
X,
Because
it'd
it would
have to
have
be
to be,
infinite.
yeah, right? So like X, no matter what X, I'm going to get close to 0, but there's no way I can actually get to
Right.
0.
You always have 1 on the top, like
There's
no.
always 1
Yeah.
on the top.
Yeah.
So that would be my horizontal asymptote here, right? Is no matter how, right, my graph's going to look kind of the same, right? My graph is the same. I'm just looking at a different end of it now. Because what I'm saying is no matter how far out I go here, I'm going to get closer and closer to 0, but never actually hit 0.
Right. Okay.
Now, when we looked at this case here, though, right, there's no asymptote because 2x does, right, equal 4 when x equals 2. Now, this is helpful here when we're talking about discontinuities in the graph and whether or not things are differentiable, because that's where we'll say does my function, is the limit coming from the left and the limit coming from the right, are they the same? Right. And so sometimes we'll see they're not, right? So here, if we were to look at negative values of x, what would we find out? It would go like this, that right, they're coming to 0 from different directions, but they do this. They're not the same. And we'll see that as you can see that in piecewise functions frequently, right? I might have one piece where I'm going this way with this one and this way with this one. And so as I come together, there's some kind of a gap, a jump between my two pieces. And so my limits are not the same. So that's another case where we use limits to evaluate that.
Okay.
Where do we see the limits in the math map? Where are they? Is there a lot of places, or is it mainly toward the end of the year?
So we introduce limits in chart 4, and we introduce the limit laws in chart 4, because in chart 4, what we do is we look at just one-dimensional limits, right? So as x approaches 3, right, we're really just learning how do we read half of that limit? Well, what's happening to my x value, right? X is approaching positive 3 from the left, or x is approaching negative pi from the right. So we're just looking at those 1D limits, which is really this part here, right? That's the part that we're looking at mostly when we're looking at those limits and graphing those in lesson 4. But throughout 328, Lee is practicing reading those limits, right? We're just practicing reading the limits so we become familiar with them. Then they crop up again a lot in lesson 11. That's where we're looking at the different functions, because our rational functions and our exponential functions and our logarithmic functions, those all have asymptotes, and we use limits. But then limits are essential in lessons 25 and 26, because that's where we're looking at an application of limits in order to define derivatives and integrals. So they crop up throughout the math map, right? This idea of limits over and over again.
Kirsty, how would you write a limit if it was not at 0? Like, what would that look like if the limit was 2 or 1 or negative 2?
Like, you mean like if I was to, so you wouldn't really see it graphically. Because if I was to look at f of x equals 2x, right? And I was to, here's my graph of f of x equals 2x. And if you just said to me, what's the limit of 2x as x approaches 2? Um, here's my 2, 4. I wouldn't necessarily graph it. It would just be something I would talk about because it's there's no asymptote, there's no discontinuity, right? So what you'll see is when we talk about discontinuities, especially, we'll say is the limit of f of x, right, as x approaches c from the left equal to the limit of f of x as x approaches c from the right, right? Or from the right and the left. I think I just said those backwards, right? So that's the type of expression you might see. And then you might say, okay, well, I'm curious about 2. So the limit as x approaches 2 from the right of 2x, I want to know, is that equal to the limit of 2x as x approaches 2 from the left, right? Now, in the math map, Lee uses some little arrows to help us to see what we're doing. So let me do those in a different color, right? So as my x is approaching 2, right? My function is approaching 4. As x is approaching 2 from the right, my function is still approaching 4. So in this case, those limits are equal. And I would say my function was continuous, right? Because my function, it's defined and my limit is the same there. Does that help any?
So
You
question
know,
then,
go ahead,
sorry.
Andy. No, go ahead.
So whenever if you're looking at the graph, if it's approaching from above, then that's when it's positive, and then if it's approaching from the bottom, then it would be negative, similar to like your 2 from the left and 2 from the right.
Well, no, because you're always going to be, we're always going to say, what's my x value? What's my horizontal doing, right? It's either going to be coming from, I might be backwards, right? So coming from the left or coming from the right, and we indicate that. And then I'm going to say, what's my function doing? And my function is going to be going to 2 or to positive infinity or to -2 or negative infinity, right? So it's going to be the value that it's going towards, not necessarily the direction that it's coming from, but the value that it's going towards. Does that clarify that?
Yes,
Like,
thank you.
okay, good.
Yes. Jill's question. F of x equals y. They're the same. You could say y equals, but as we move through algebra, we start to say f of x, because what if you have x, y, and z in your equation and you want to specifically look at only one of them? So you tell, and the f of x says that's what I'm going to look at right now. Versus you still could just say y equals these equations. I'm glad there's memes about f of x equals y. Math is very funny.
I'm excited to actually get the jokes now because I've seen some. And then now I'm like, I'll send one to Kirsty and say, this is so funny. Like, I actually get this now.
Good. You don't need to be excluded from all forms of humor.
Right.
I mean, like the square root of -1, 2 cubed, with the sum symbol, and then the pi.
Yeah.
That one I just got.
This one?
That one, right?
Yes, on a pumpkin pie with a piece of it cut out.
That's good timing to get that at Thanksgiving.
Right? Exactly.
What are the
Right.
questions you guys have? That was good.
The question from week 13.
Good.
Specifically like page 2 at the bottom where your measure of angle ABC versus, I guess, is that the measure of arc ADC? Is that how you would read those things?
Yes.
Okay, so then my question would be like for the third one over, like the measure of CAD. No, sorry, CB. Sorry, trying to
That's
read my
okay.
daughter's handwriting. Um,
So you have to have 3 points so you know which way to go around the circle for the arc, because you could go the short distance, which is the minor, or the long distance, which would be the major.
right. How do you figure that out? So it's like the third one, the farthest one to the right, the measure of angle CBD.
So
Oh,
I
I don't have.
think, yeah, so I've got it.
Good.
And I think what we have done to clarify that for next year is I'm just going to move this over so then everybody knows what we're talking about. So we have, I'm going to draw the picture and B, A, C, D. And then we're asked the measure of angle DBC, the measure of arc DC, the measure of angle CBD, and the measure of arc CAD. So unfortunately, there is no good way to indicate the reflex angle. So the first one, when we see DBC, we're going point, vertex, point, and it's 135 degrees. And these are central angles. And so the intercepted arc, this is DC, is 135 degrees. And then what happens is here we see that this says CAD, and that's telling us, as Lee just pointed out, we're looking for this major arc because we have to go through A. And so now
Just,
we have,
Kirsty, hold on. You wrote the measure wrong, so it's confusing when you say that. Look at what you wrote.
which one, what,
You wrote CBD, but you said DAC.
oh, okay, well, I was talking about the arc.
Okay, so it's just in the line with what's written. Keep
Okay.
going.
Yeah. So this is, I'm just pointing out that if you look at this measure here for the arc CAD, which is our major arc, it goes through A, it has 3 letters. That measure is going to be 225 degrees. That is the only hint as it's written that what we're looking for is this reflex angle here, CBD. So what we've done next year is this is actually written in here, reflex, to indicate that what we're looking for is this reflex angle. And so it would have the same measure because it's the central angle of that major arc. So does that help, Amy? Sorry. I just realized I thought it said Amy and then it says Andy, and I'm not sure if that's you or if that's so sorry if I'm butchering your name, but does that help clarify that?
Yes, that's very clarifying. Thank you.
So, with the errata sheet and all the corrections, when is the next edition of Complex? So when can I tell people to, if they want
So
to?
so the next edition of Complex will be in April. There will be an updated version in April. And unfortunately, we know based off of just the fact that the first couple of years of anything, there'll still be errata, but there will be an updated version of Complex available in April, along with digits, integers, and fractions,
Okay, thank you.
and monomials.
Thank you.
You're welcome.
If you have an updated version, are you only putting clarifying things like that? Or if there are parents who went ahead and bought like an extra set because they were expecting a sale, will they still be able to use last year's or this current year's next year so that the problems are the same, just anything clarifying might be different?
Yeah, I think, and Lee may have a better answer. Some things, because of the nature of the math map, right? Complex doesn't stand alone. So as Lee has worked on monomials and fractions and digits and all these other levels, right? She's seen some things that maybe, oh, wait, this would be better. And so she's adjusted things in complex to better fit into that. You can absolutely use the current complex next year, right? But there are probably going to be some times where you're going to notice that, hey, just like any other textbook, if you have an older edition, you're going to notice that there's some things that don't line up perfectly.
The thing that will always line up perfectly, Lord willing, is the bars are exactly the same in each edition because we haven't changed the map. But yes, if we find an error or we go, ah, that was a better way to teach that, I'm going to change the problem for the next edition to keep improving the curriculum. But it'll still be the same kind of problem. It might be you read it left to right instead of up and down to fill in the chart, or it might be a different part of the problem needs solved, but it'll still be the same kind of problem.
So does that mean that the digital versions would have those updates on them, that if we're looking at a hard copy and we have a question, we could see a difference on a digital version?
Yes, once I think it's June 1st is the magic date that we sort of swap from one academic year to the next in CC Connected. When that happens, the lessons in CC Connected will be updated. The companion will be updated to the latest version of the lessons. So
You can always imagine that the so-called free versions that we're letting out until they're printed, those will never be the absolutely latest and greatest because they're still being worked on to get better and better for that print date. But they will be like naturals next year will be far better than naturals 3 years ago. So we're trying to use technology well, but we also know that we have print deadlines.
And it is not always perfect, but we do actually try to keep the charts that are in the companion up to date. So if I make an edit in the charts today, you don't have to wait till April to see that edit. So you can always go and get close to the latest version of the charts in the companion, but the lesson pages themselves, that will happen in June.
Kirsty, do you remember my email to you about the charts and the digital copies? And I tried to explain it in words, and I think you
Yes.
understood what it was I was saying. Is that going to happen anytime soon so that we get a better picture quality?
We've tried to figure out what's going on there, and we don't really know what's going on there. So we're still trying.
Okay.
We're still working
Okay.
on some of those things, and trying to figure out why some things don't come through always as clearly. So
Okay. All right. Thanks.
I have another question if I'm not
yeah, no,
asking
that's
too
what
many.
this time is for.
Again from week 13, the conical or conic section analysis. Is that how you pronounce it?
Conic, yeah.
Conic. Okay, so like page 7, how do you determine the A value to be positive or negative, especially like in the second one where it's the way it's graphed, it looks like it's on the negative side?
So A and B should always be positive. let me look at the answer key, and maybe that will help me to see what you're referring to.
They both show as being positive, but like the one on the right side, it looks like it's in the negative, like X would be negative values. So I'm just curious if there's like a rule or a law or something like that that says that they need to be positive.
Okay,
Andy,
so
you're looking at what? Tell us what page, week 13, page what?
Page 7.
Okay, thanks.
okay, and you're saying the right hand exercise?
Yes.
Okay. And what is it that you feel should be negative and isn't?
Well, I'm just my daughter had a question as to like because it's the A value, the way it shows on the ellipse,
Yep.
it looks like it would be negative because it's past the Y
Okay.
line.
So the A and the B are distances. They're not coordinates. So so that's why my H and my K are both coordinates. So they're telling me where it is in the plane. So that's why my H is negative, because it is, right? It is in that second quadrant. But the A and the B are both telling me a distance, and they're telling me the distance from the center to the edge, right? Horizontally, and then the distance from the center to the edge vertically. And so since it's a distance, it's always going to be positive. It wouldn't matter if I took that ellipse, I could put it anywhere in my coordinate plane. My X value, my H value and my K value are going to change because that's what's telling me my position. But that A and that B would never change. As long as the size and the shape didn't change, that A and B are going to be the same, and they're always going to be positive because it's a distance. Does that help clarify that?
Kirsty, I don't think that's something I addressed. So I'm going to go. Thank you very much, Andy. I'm going to go back and see either in the frame or in the lesson. It's almost like the A, B somewhere needed to have an absolute value sign or set it equals D or something. So I thank you for asking.
Yes,
It is in
that's
the
the
charts. Yeah,
Sure, I
it
know
is
it's in
in
the
the
chart.
charts. If you
Mhm.
look in the chart, we'd say, we talk about the minor axis and the major axis, and we're
Mhm.
looking at it there as a distance. So that's what's going on there. Does that help to clarify that?
Yes, that's very clarifying. Thank you.
You're welcome. All right, I am going to go back here, and I'm just going to go give you a couple of things we thought we would share with you today. But if you have more questions that this generates, please feel free. This time is here for you. But here's a question for you. As you think about most of us taking some time off between Thanksgiving and New Year's, right? However that looks for your family, we know now, right, that our mathematical thinking doesn't end with the closing of the blue book, right? And so this is some ideas that are from chart 30, chart 4 from lesson 30, of some ideas for how maybe you could continue to practice math, even if you're not using the booklets. And so I would love to hear your own ideas, either something that's generated by this list, or do you have any of your own ideas? What does your family do to continue to practice math when you're not actually in your textbooks?
I know we're going to be working through those notation note cards.
I suspect a lot of people will get games for Christmas that have strategy and proportions and calculations with them.
I know cooking is a very obvious one. It might be on here somewhere else, but that's such a practical one. And when you're one and a halving a recipe and then changing from teaspoons to tablespoons and ounces to, we've been getting the scales out and using like grams and ounces and trying to kind of get an idea of what their proportions are. So if you are given grams, you might know approximately how many, like it's just getting familiar with those conversions.
Our community just had a maker's market. So this is the first year that my kids can actually do things from the beginning to the end, including opening in the oven, pushing it in, and do a bake sale. And then I took them to the grocery store, and they realized that eggs are actually about close to $4 a dozen, and they realized that they're not making any profit. They're actually losing money by hosting a bake sale. So they're using their math that way. It's really cute.
It's discouraging too.
Hey, that's life. That's life.
Yeah, I was going to say grocery shopping in general. That's one where we practice doing math and looking for deals. And if it says, 4 for however many, is that less than actually buying one by itself? And just doing those different calculations through this time.
Yeah. Somebody mentioned games. I just bought 3. Now, I don't know anything about them or if they're good or anything, but this one is called Proof. And this one is called Absolute Zero. And this one is called Vin.
Yeah.
And so I'm going to force my family to play these over the break, and I'll let you know how they turn out.
Yeah. But Babs, 5 years ago, you probably would never have bought those.
No.
Right. Great. It's so great to see your enthusiasm. Something that you can do with your littlest ones. My April is really good with the 3 kids on time and helping them to appreciate time early. And so, like, she just has a language she speaks with them where she's saying, well, how many sleeps is that? Or how many innings is that? Like, she finds things that they know and uses that to measure time instead of minutes and hours, and then eventually converts to that. So, something we could even do over the holidays, and especially with the blessing of the eternity of eternity coming here to the finite, it's just maybe work on our basic language and increasing it with some math terms.
I was just thinking about if you decorate a Christmas tree, especially with older children, right? And you could do it with younger ones, but older ones, you could always challenge them to come up with different symmetries for decorating the Christmas tree, right? So you could do some reflectional symmetry, you could do some rotational symmetry, right? So
how many degrees from Santa did you just put the reindeer?
You could also do that with decorating sugar cookies.
Yep, I like that.
We do different kinds of symmetry.
Yeah, I'm going to come to your house because your house sounds like you're doing lots of baking. And so I think we're just going to all come and hang out there.
You're all welcome.
Especially we don't have to buy the eggs.
Maybe Jana gets a discount.
We have 50,000 chickens, but they're not egg layers, so.
Oh no.
Oh.
Yeah, but there's a lot of ways, right? Just in the way we live our lives every day to continue to talk about mathematics. And even just introduce some of those algebraic skills, right? I know a lot of you have older students, right? So figuring out unknowns, right? So Jana, if you're not just calculating, right, but having them say, okay, well, what if we were to write an equation to convert from one thing to another, right? And then solve for the equation. How would that, right? If I know that 4 ounces, right, equals, and I don't even know, right? It depends on what it is, but I'm trying to think, like a quarter of a cup of cocoa is 32 grams. Okay, that's from one of my favorite recipes. And a quarter of a cup of cocoa is 32 grams. So I could say, well, so if X is my number of quarter cups, right? So now I have like 32X equals something, right? So I can start to play with that with our older students to start looking at some of those algebraic skills to work that in there. Or if you were doing bake sales, right? Well, what is it that you would have to charge, right? In order to break even, or what would you have to pay for your eggs in order to break even, right? If you were going to go and ask somebody to sell you eggs from a farm and you're trying to negotiate, right? Maybe you could solve for the price of eggs and go and say, hey, would you, instead of charging me $4 for your eggs, would you be willing to charge me $3.75 so I can still make a profit at my bake sale? Right. So there's ways that we can bring those things into these everyday activities, even with our older students, to help them see where maybe they are thinking algebraically, even if they're not always writing it down and making it look like algebra. So think through those ideas, because next week I'll have the other half of that chart to share with you. So if you come up with some ideas between now and next week, we can share those. And then the other thing that I thought I would share with you this week and next week are a couple of examples of the Seeing the Unseen booklets, or examples of things that might be included in a Seeing the Unseen booklet. So Jill, are you still on here and just hidden, Jill?
He's there.
Okay,
Yes,
there
I'm
she
here.
is. So I'm going to show you some things that Jill sent me from her Seeing the Unseen booklet this week. And next week, I'm going to share some things from Babs's booklet. Jill, feel free to narrate. I think I have 3 slides. And so feel free to narrate and tell people why you chose what you chose to put in. But one of the things that we've asked tutors to do is either on week 15, or if you didn't get it done week 15, on week 16, to show an example to your classes of what that Seeing the Unseen booklet might look like. And so that's what these examples came from. These are examples that they did to share with their classes, to encourage their students to be looking for things to add. So here's the first slide of something that, and I'll let Jill narrate and talk about it if she'd like to.
Well, I sometimes try to do a variety of things in my blue books, or not my blue books, my Seeing the Unseen booklets, to show students that they don't have to put in a math equation. They can just put in a math thought they had, anything that they thought about numbers. So even in class, we'll talk, we looked at the fact that that book exists and that it's blank. We didn't spend a lot of time with it, but throughout the year, if they say something about one of the books we're reading or something during math, so frequently I'll say, oh, that would be great to put in your Seeing the Unseen book. And I usually have Post-its out on the table. So I can say, just jot down a word that'll remind you, stick it in your guide. And when you go home, that might be something that, even just sticking the Post-it in your Seeing the Unseen book so that you can write about it later. But just the ideas, and sometimes when you read them later, they don't feel as big as they did at the moment. But at the moment, you can be thinking, oh, how big God is. Oh, wow, there's just every dimension. We talked about orthogonal, so I might even later have more words about there, like orthogonally, all these different dimensions, and God is already there. And no matter how much I zoom in, he's still there. I could put another 0.5 and he's still there. And I think if I spent time talking about this with my family, then I might start thinking about how water fills in all the cracks, or how snow really fills in all the cracks of the trees, and I might add that to my blue book. So it can be a conversation starter with something small or some big thing you're just thinking about. And just, I think I was looking up number facts, and one of the ones that popped up was that 1,000 is the only number that has an A in it, from 1 to 1,000. And I thought that was such a cool little piece of trivia. So I stuck that in this one also. And then, of course, I had to think through, and I'm like, wait. And then I thought, oh, I don't actually have to spell all these because the words get repeated.
That would be a great thing too for your interesting integers.
Oh, yes. And then I sometimes stick things in my book. I love Post-it tabs. I have so many of them, all different kinds. And I like that they're so structurally, like all the funny shaped ones, I don't use those. I really like the arrows and the straight ones, and I like them all lined up. And so I put those in there. And I had so much fun with the look and say sequences that I learned from Kirsty. And I think I've even asked her, different times, remind me of that, remind me of that. So I'm like, I'm not forgetting it. I'm putting it in my my book so that I can find it and refer to it. And then just some jokes because, it's always nice to have a few math jokes there.
Well, I really liked the Roman numerals, Jill. I had not heard that one before. So that one, I like that
Oh,
one.
good. They did one in a math camp years ago in a practicum, like probably in 2018 or 19. And it had when is 4 half of 9?
When you're a Roman.
Yes, when it's a Roman numeral and you have, the X and the I and you cut it in half, it's a IV instead of an IX. And so you just have to cut it the right way. It was really cool. I probably should have put that in there too. But if you've never done the look and says, they're really fun. And then just these are some coasters that my mom made, and I like all her quilting. I don't quilt, but she does, and so I put some samples of that in there. And then just my question, I guess I was watching the rain and thinking, so I guess with wind they wouldn't really be parallel, like they would have some curve, but do they follow the same path? So just kind of neat. And then I was just thinking about math and where is there math in different places. So just sort of doodling and writing down almost like a topic wheel, but not. And so instead of just making a list, I thought, well, my page might be a little more interesting if I draw some wavy arrows instead of just a list of places that I like math. And I like the rhythm of poetry. And so I named a couple of the poems I like. And then I really do love pie, also math pie. So
I don't think I've ever heard of corn pie before.
oh my goodness, it's so delicious.
Is it a savory thing?
Not really. It's a Pennsylvania Dutch thing. So my grandmother was Mennonite. And so corn pie is, you don't need a bottom crust. You just put it in a pie plate with, I use frozen corn and butter and hard boiled egg, which I know sounds a little strange, but a bunch of hard boiled eggs, and you chop them all up. And you have the butter and you have salt and pepper, and you put just enough milk in there that you sort of start to see it peek through, and cover it with a crust and bake it. And it's like a corn side dish with a buttery crust. And I love it. And so my grandmother always made it for me.
That's awesome. Well, thanks, Jill, for sharing. I love that you had so many different a variety of things and they were all really accessible. So it really emphasizes that this is not supposed to be um, it's not supposed to be a Faces of History project,
Yeah.
right? This is just a record of what did you see this year? And like Jill said, I love the look and say sequence, and I wanted to remember it. That's the kind of thing that students can be putting in this booklet.
I one time I was actually working on a Seeing the Unseen booklet, and I was sitting on a rocking chair. So I was thinking about this rocking chair, and I thought, oh, I could draw that. I've learned a few things with oils. I can do some straight lines and draw a rocking chair. Then I started thinking, I wonder if there is math to rocking chairs beyond what I'm imagining. And I looked it up, and there actually is a perfect ratio for a rocking chair for any human. If you know how tall you are, you can find the ratio and have this perfect, like, breathing whole everything with your rocking chair.
Jill, now I want my perfect rocking chair with some corn pie.
Yeah.
That's what I'm gonna like fantasize about. It's just sitting
Ask
there
for
perfectly
Christmas.
One of
rocking.
those things.
Ask for Christmas.
Right. I'll do the corn pie if someone in your family will do the rocking.
So just a reminder, the next 2 weeks we're still doing our Q&A. So bring your questions, bring the things you want to share. And then in January, we'll be jumping back in to lesson 18 on January the 8th. So, and so we've got a few minutes left. Are there any questions that didn't get answered today? Or anything that anybody wants to share?
I just have one more quick question. The using the compass and even like the safety compass, doing the arcs and stuff like that for week 14 is causing frustration because they're not exact. I encourage my daughter that it's okay, you're not a professional, you don't have a professional tool set. Is that okay? Or like, should I encourage more towards exact copies?
No, eventually, right? We're all moving towards perfection, right? That's our goal is to be perfect as our Father in heaven is perfect. But then we know we can't be perfect, and that's why he sent Christ, right? We need Jesus because we can't be perfect. Um, so yes, that's the goal. Do we expect that from 12-year-old fingers? No. When you look at that booklet, the one of the things we really hope you take from that is you're gonna at different, right, folding patty paper may be easier for some students than for others. Using a compass might be easier, using a ruler might be easier. But a lot of the goals the first few years, even into the challenge years, is just working on the tools and developing the discipline to use those tools, right? We don't expect anybody to jump in and be perfect. Now, by the time that they're finishing up, hopefully a lot of them will be starting to achieve that external physical discipline that lets them use a tool precisely. But it takes practice. And so that's, yeah. So that's why there's so much tracing. That's why there's so much like try to copy this, because it really is about practicing with the tool and not actually doing the construction.
Imagine how it used to be. Well, Kirsten didn't have to imagine, she did this. Imagine how it used to be to navigate on rough sea with the tools that they would have had 100 years ago. And yet they did it. So it's patience and practice. And notice it's at the end of the semester. We didn't want to burden the tutor or the child with more facts to learn, but wanted to make sure they had an opportunity to practice some of the artistic elements of mathematics as they prepared for the blue book, so that hopefully it would be more fun than work, and yet it's very purposeful.
Thank you.
You're welcome.
I thought lesson 14 was the funnest lesson ever. I did have a couple questions on 13 if there's time.
Yep.
So I'm on page 6 and of lesson 13. And I really struggled with the middle section in the bottom frame, name the tangents. So I can name tangents, and I did that. And then name the angles and arcs of the indicated vertices. A vertex outside the circle is the intersection of a tangent and a secant at B. And I understand that. What I don't understand is how we got those particular arcs of A and C, and then it was AFD. And I don't understand that.
Okay, so let's see if I make sure I got the right question. So you're on page 6 and you're talking about the middle one.
For the Lord is your inheritance. Hold on. Therefore, hope in him. Say again, everything's turning on all at once and I can't hear you. Go ahead.
Okay, so we have, I think this is the one you were asking me about. Oops.
Correct. Yes, the middle one.
Okay. And pretend that is tangent, right?
That's a secant. Secant, yes.
G, this is A, E, C, D, F, and H. Okay, so there's our picture, and you were asking about the angle and the arcs. So it says the vertex outside the circle is that in this particular case, right, we're not talking about all vertices, but this particular case, that the vertex is the intersection of a tangent and a secant at B. So here's my point B. And so I've got a tangent, which is this line here, and I've got a secant, which is this line here. And then it says, what's the angle? So there's a lot of different names we could give that angle. So I'm just going to give you some of them in case your child happened to come up with one of the ones that wasn't listed. Because we could have had G, A, B, sorry, not G, A, B. What did I just do? G, B, C, for example. There we go. We could have G, B, D. I could have A, B, C. I could have A, B, D. Then I could also reverse all of those, right? So I could have had CBA and CBG and DBA and DBG. So there's all of those different possible names for that angle, but we're all talking about this angle.
Got it.
Then it says, what are the names of the arcs? The arcs that we're looking for are the arcs that we're intersecting with those two, right? So there's this arc right here, which is AC. And then the other arc is this arc here that goes from A to D. And I'm going to go through F. So those would be my two arcs that are being defined by or intercepted by the angle, right? That tangent and that secant. Does that answer the question?
Well, I guess, but so I guess the main thing is you're leaving out the portion that the secant cut off the side of the circle. Okay.
Yeah, because what happens is that when we find the measure of the angle, the measure of whichever name we chose, right? Let's just call it GBD. The measure is going to be half the difference of the arcs. And so it would be the measure of arc AFD, which could have been DFA, just so we can go either direction, minus the measure of arc AC. Right? That's how I would find the measure of the angle. That's the relationship between the arc length and the angle in this case.
Oh.
And so that's what we're pointing towards eventually, is being able for the students to be able to solve those equations and recognize that. And so that's where we're interested in just those two particular arcs, the ones that are being cut off by that angle.
Thank you. Because sometimes the kids ask me, so what did you struggle with last week? And sometimes I say, well, I didn't, but this week I do. So I will be happy to share this with them. So,
oh, great.
Thank you. And then there was one more in week 14. I'm so excited about this lesson. I've gone through so much patty paper. It's just unbelievable. But on lesson 14, page 6, I was a little confused by the DE4 square number 2.
Yes.
I don't understand how you can just automatically
can't
double-sided thing and get the parallel. I know how you could do it if you're making the parallelogram and all that kind of stuff, and that was really fun. But I don't understand how you can get that here.
Yeah, you can't get that here without actually constructing a perpendicular. So you would actually have to go back and use either DE1 or DE2 to actually make sure that that's perpendicular. But some of the steps were sort of abbreviated here. And that's one that was abbreviated. But that's where, yes, you would need either DE1 or DE2. And you can see underneath that, right? It says, how do you know it's perpendicular? Because you can use DE1 to find the perpendicular bisector, and then you would be able to show that you were perpendicular. So that's what that note underneath is really trying to point out, that you have to go ahead and go back to DE1 to make them perpendicular.
Okay, and I kind of understood that, but when it was just turn the DES a perpendicular line, I'm like, No way. No. No.
Yeah,
Okay.
maybe it would be helpful if the 3 wasn't there, and that way you would see that that instruction was part of step 2.
It may be.
Yeah.
Okay. Thank you so much.
Oh, you're welcome.
And I'm making a note to look at it, see if there's any more we can clean up. So one thing that's absolutely true is there were a few steps left off in real complex and monomial that are in binomials, because we were still trying to make the space so the child could write right on it and see the pictures of the tools, and just trying to have the tools very clear made it so all the steps just didn't fit on the page. But when we go to the next smaller font size and we're more concerned about the actual construction and not how to just use the tools, we don't have any steps skipped.
Excellent. Thank you.
It's kind of like, if you look down at the digits, naturals and integers, there's a lot of steps skipped, but nobody will care because they know they're little kids. It's that transition where the mama or the child starts to care. It's kind of hard to get right because everybody's different.
Well, this is just such a cool lesson. I remember in high school we got to do the thing where you have the 2 points and how do you find the median of those 2 points on a line. And I remember thinking that was so fun, and that came back, but all this other stuff that they just neglected to teach us. So my, childhood brain is coming out going, oh, tell me more, tell me more. So I really enjoyed this lesson.
Great. Well, you guys, great job today bringing the questions. Please bring more for next week. And we'll look forward to diving deep into other math concepts. And until then, have a great week and happy Advent.
Thank you again so much.
Thank you. God bless you. Bye.
Thank you. Appreciate your time.